Section 5.3.4, the inseparable case, soft margin classification. When the dataset is inseparable, there would be no separating hyperplane. Therefore, there is no feasible solution to the linear supported vector machine. Let's see this figure. One of the negative data points is the other side, and one of a positive data point is far away. In this case, there's no separating hyperplane, and the optimization for the supported vector machine will not converge. Now let's try to fix it so that the algorithm can handle the inseparable case. The new formulation will involve the slack variable. The slack variable allows some data points to fall up the margin, but with some penalty, and so that we allow to make a misclassification, but we have to pay the price. The motivation for introducing the select variable psi is here. First of all, the linear constraints need to be relaxed for inseparable data. Secondly, we allow the optimization to converge on the appropriate cost penalization, but although some points are misclassified, such a strategy of the supported vector machine is called the soft margin classification. Let's do it mathematically. First, we call the linear supported vector machine formulated in this equation minimization of W norm squared subject to that inequalities defined on each data point. Now, in soft margin classification, first of all, we relax this constraint. It can be now moved to the other side so that this portion is larger than or equal to 1. Now, rather than 1, we put 1 minus psi I non-negative. So this constraint is relaxed constraint. Now, for this relaxation, we try to put on the objective, so it becomes a part of cost. Now, along with the C, we control the relaxation. But that is now the new objective function for soft margin classification. Once you try to choose C very large, that means that now here psi I will become small. That means now this relaxation is small, so that the final model will be tight, like in this left figure. And if you choose C small, then now psi can be large, which means large relaxation, so that here one of these points can be the other side, so that this soft margin classification is making such kind of a separating hyperplane, and one of them is misclassified. So in that way, by choosing the variable C, you can control the strength of the relaxation. So by using C, you can tune the bias and variance, and eventually C is the parameter for the bias variance trade-off. Okay. Here we say the constraints allow some slack of size psi I, but we pay a price for it in the objective. That is, now if it's larger than or equal to 1, then now here psi I will be 0, so that there's no penalty. Otherwise, now the value is 1 minus psi I, and now psi I is now on the objective, so that we pay a price psi I positive, right? Okay. Now, for the new objective function, we should introduce Lagrangian. Okay. That is now original new object function, and we have here constraint. This is now, okay, this portion is larger than or equal to 1 minus psi, and psi I now non-negative. We have these inequalities. For each I, it is defined so that, and now I is moving from 1 to n is the number of data points. So we have 2n inequalities. So for each of them, we try to introduce now Lagrange multipliers. For this one, alpha I, as we did earlier, and we introduce Ri, Lagrange multipliers, so that we get the Lagrangian in this form. This is now the original new object function. Then along with the Lagrange multiplier, that slack variable is now summed and subtracted, and along with alpha I, now here, that we move the right side to the left over there, and then multiply alpha I, another set of Lagrange multiplier, and here contributed. That's the Lagrangian for the soft margin classification. Now for this Lagrangian, again, here maximum over, okay, the primal problem can be formulated in this way. That is now maximum, that is minimum. Okay, let's go to back here. Okay, so that is a minimum, and over W0 and slack variable, and maximum over alpha and R. Now, that is the primal formulation, and its dual can be made by changing the order, so that now becomes maximum problem. First, we try to get the optimization for minimum of the Lagrangian. And now we are using, again, the same way, the KKT condition, and here simplify. Then we reach this dual problem. Okay, so after some work, the dual turns out to be this one. Okay, this dual problem of the soft margin classification is really almost the same as the original dual problem. Only the difference is this portion. Now alpha I is bounded by here C. So here we can say that the only difference from the original problem's dual is that alpha I is non-negative. That condition is changed to here alpha is between 0 and C. So it's quite neat. In practical implementation, it's not much changing. So only using this another inequality, we can solve the problem. So it's quite neat formulation. And in the last section of the last subsection of the section 5.3.6, will try to solve the problem by using SVM algorithm. Okay. And now for the SVM, including the software margin classification, let's try to express the algorithm algebraically by using metric vector notation. Here we define Z, that is now the data times the label. Okay, that is Z. So that if data is in m dimension, then this is n by m dimension, and 1 is just a column vector including every 1. Then the dual problem can be written, okay, this portion will be alpha dot 1, and now that portion, okay, this can be expressed in this way. Here alpha dot 1 and half, and now alpha transpose Z and Z transpose alpha, and subject to alpha dot Y equal 0. That is exactly this one. And then here we have the constraint for alpha I. We write down here. Okay. Okay. So the dual problem can be written in this way. In this expression, G is the Gram-Schmidt defined as GZ times Z transpose is a metric in n by n. So here Gij component are here given in this way. Xyi, Yj, and Xi dot Xj. Here, this problem is a typical quadratic programming problem, and it admits a unique solution. Here we summarize the supported vector machine. In training, we compute Gram matrix and solve for alpha, and once alpha is gotten, the optimal value, then we can compute weight W, and that is the first KKT condition. Now we can get W0 optimal value, 1 minus minimum for the yi equal 1, and that dot product. Okay, we can get here and W and W star and W0 star, and also in alpha star. And in classification, here once a new point comes, then for each xi we make a dot product, that is ki. Now by using ki we try to make that, but that is the same as, in fact, this net input. We try to get here net input for given x. Then now net input is computed, then we try to test the sign, so that if it is positive, then and now prediction is 1. If it is negative, then the prediction is -1. But here, the reason we are using this one is that now alpha I is mostly 0, and then only it is non-zero when the xi, the corresponding xi, is supported vectors. That means that on the boundary, so that this computation is much simpler than this net input. So here, after computing alpha star, we try to keep the positive alpha I, and now for the corresponding the corresponding I for xi, we can compute this one, and then we can organize this value. So it's much cheaper. So that's the reason we can use this formula. But basically, this is the net input. Okay. Okay. We'll continue in the next part. Thank you.